Okay, derivatives of exponential and logarithmic functions, part B. So here are some properties of natural log functions that you should already be familiar with. These also work with log, log. Um, Obviously, the natural log of 1 is 0 because the graph for the natural log, okay, the log graph, or natural log, sorry, look a little something like this, okay? So at 1, it hits the x-axis, so that's 0. Okay, if I have a natural log of two functions being multiplied, or two numbers, I can add them instead. If I have a natural log of something to a power, I can bring that power to the front and multiply it by the natural log of that something. If I'm dividing two things, I can turn that into subtraction. Okay, this should sound familiar. Okay, so we're going to start off by using these properties. Example 1. For a, it says the natural log of 10 divided by 9. So we're expanding. We're going to write these using the properties just discussed. So this is equivalent to the natural log of 10 minus the natural log of 9. Okay? B, I have the natural log of 3x plus 2. So what I'm going to do is I'm going to revert this to an exponent instead of the square root of 2. It's at this point you should be able to do that automatically, right? 3x plus 2 to the 1/2 power. Square root is to the 1/2 power. They're the same thing. Now that I have rewritten it with an exponent, I can use one of my properties that allows me to bring my exponent to the front, and I'm going to multiply. So this is 1/2 times the natural log of 3x plus 2. Now notice, I'm not deriving anything. This is just rewriting using rules that you learned in Algebra 2 and Pre-Calculus. Okay, part C. Right about there. So I have the natural log of 6x divided by 5. Now, you can write this as so. The natural log of 6x, right, that's the top, minus the natural log of 5, which is the bottom, the denominator. And, of course, the 6 and the x, if you look, they are being multiplied. So you could go even further and be the natural log of 6 plus the natural log of x minus the natural log of 5. Okay, now the reason for expanding natural logs, or rewriting them rather, is because the rewritten version is usually easier to derive. Okay? All right. I think that's that. Okay, derivative of the natural log function. Okay, so for the derivative of natural log, let u be a differentiable function of x. So the first one is just a simple old, taking the derivative of natural log of x. And the derivative is going to be 1 over x, always and forever. That is the derivative of natural log of x. Now, that's the most basic equation you can have. So when the equation becomes more complicated, as on the other one over here, natural log of u, so u is some kind of function. It could be 3x squared plus 5, or 5x cubed minus 10, something like that. So then the derivative becomes u prime over u. Okay? Now notice, this is also u prime over u. If x was u, right, the derivative of x is 1, that's why it's on top, and u is x, so it's on the bottom. Okay, example 2, part A. So here I'm deriving the natural log of 2x. So the derivative, right, is going to be u prime over u. Obviously, the stuff inside the parentheses is u because that's what the natural log is of, right? So u is 2x. Okay, so u prime is 2. That's the derivative of 2x. My derivative is going to be u prime over u. So the derivative of u over u. And that's my derivative. And of course, I can simplify that because the 2's cancel out. And voila, it is 1 over x. That's simplified. Okay, b. All right, so I'm deriving the natural log of the quantity x squared plus 1. So once again, the stuff in the parentheses is my u, right? You can even write it if you need to help you. X squared plus 1 is my u. Okay, so my u prime is going to be the derivative of that, which is just 2x. So my derivative is going to be u prime, which is 2x, over u, which is x squared plus 1. And that is my derivative. All right, part C. Oh, there is no part C. Moving on. Okay, example 3. I'm deriving again, but this time I have x times the natural log of x. And these are two functions being multiplied, so I'm going to use the product rule. Okay, so this is the product rule, just with natural logs. So product rule. So let me list everything out, right? So u is going to be x, u prime is going to be 1, right? Because this is u times v. V is going to be the natural log of x, and v prime is going to be the derivative of that. And if you look back at your notes, the derivative of the natural log of x is 1 over x. Okay, so I have all my pieces. So now I'm ready to derive. So this equals u times v prime plus v times u prime, which is a 1, and I'm not writing that down because I don't have to. And there's my derivative. Now, you should be able to see that you can simplify these x's. They do cancel each other out. So my answer is just 1 plus the natural log of x. All right, part B. So I'm deriving ln of x cubed. So this is actually a chain rule. Okay, how do I know it's a chain rule? Well, there's an exponent and there's stuff inside of a parentheses, and that stuff is its own function. The exponent makes another function. So I can rewrite this as something to the third power. You can use u if you like, right? I could rewrite this as u cubed. So if this is u, okay, u cubed, derive that. At this point, guys, we should be able to derive powers like there's no tomorrow, okay? Quickly, without giving it a second thought. If not, then we need to work on it. So 3u squared, that's the derivative of u cubed. But because u is actually another function, it's an entire different function, I have to multiply by the derivative of u. Now, if it helps you, list out your u and your du. U is the natural log of x. Du would be the derivative of that, which is 1 over x. So now I know what my u and my du are. I'm going to plug them in. So I get 3 times u, which is the natural log of x, squared, times 1 over x. And the only thing I would do here is I would just rewrite it slightly so that it's all together with the x as the denominator. Okay, that's valid. All right, moving on. All right, example 4, rewriting using properties of natural log. So we're going to rewrite this before actually deriving it, okay? So, again, I see a square root. Automatically, I should be thinking that is to the 1/2 power. So to rewrite this, it's going to be the natural log of x plus 1 to the 1/2 power. Now the properties of natural log lets me grab that exponent and bring it to the front, and I'm going to end up multiplying. So I now have 1/2 the natural log of x plus 1. No exponent anymore, right? Because the exponent became a number. So that is the equation that I'm now going to derive. So f prime of x is going to equal, all right, the 1/2. That's just a multiplier. So I'm going to leave that right there in the front. That's just a scalar. It's a number. It's a coefficient. No big deal. 1/2. Now, natural log of x plus 1. So the derivative of anything that it has a natural log is going to be u prime over u. Or rather, this stuff in here, right, as the denominator. So x plus 1, that's my u. And then my u prime would be the derivative of that, right? So the derivative of that is just 1. So this is my answer. This is what I end up with. I would make it look a little prettier. So 1 over 2, and then x plus 1. That works. If you want to distribute the 2, go for it, but I think that's good enough. And that's that. Moving on. All right, benefits of applying logarithmic properties before differentiating. Okay, so look at this equation. It looks hideous. It is horrible. The top is a product rule. The whole thing is a quotient rule. The bottom has a chain rule. The top has a chain rule in it too. So before we start crying, simplify it. Okay? Simplifying it using the properties. The numbers are being divided, so that means that I'm going to actually subtract them now. And then the x and the quantity x squared plus 1 squared, that's being multiplied. So now I'm going to actually add those, right? Because multiplication changes to addition and division changes to subtraction. Not only that, but I have exponents that I can move too. So I'm going to rewrite this. I am not deriving. This is rewriting. Okay, so the natural log of x, that's my first term. It is being multiplied with the x squared plus 1 to the second power. So I'm going to add it to the natural log of x squared plus 1 to the second power. Okay, now this stuff is being divided by the square root of 2x cubed minus 1. So I'm going to subtract the square root of 2x, or sorry, the natural log of the square root of 2x cubed minus 1. That square root, I should be thinking in my brain, I can change that to a 1/2 power. All right, so this was the first stage of rewriting. The second stage involves bringing these exponents to the front. They're there, so I should move them, make my life easier. So now I have the natural log of x plus 2, I don't know why I wrote 1, holy crap, equals the natural log of x plus 2 natural log of x squared plus 1 minus, bring that 1/2 to the front, the natural log of 2x cubed minus 1. Now the idea is that by rewriting it, this equation is now easier, much easier to derive. So this is the function rewritten, okay? All I did was rewrite it. That's all that's going on here. I have not derived anything, okay? Anything has been, rewrite it. Nothing has been derived. Okay, now that I have my new function rewritten, and I've made my life easier, I'm going to go ahead and derive it. So f prime of x equals, because notation is important, so I know what the heck I'm looking at. Some of us are not very good at notation. Okay, so now I'm going to derive the natural log of x. This right here, the derivative of that is 1 over x. Plus, now I'm going to derive this. The 2 is just a multiple. It's a number. It's going to stay right there. So 2 times the natural log of x squared plus 1. So the derivative of the natural log of x squared plus 1 is just going to be u prime over u. Okay? So u is the x squared plus 1. Okay? And then on top of that is going to go the derivative of that, which is 2x. Okay, minus. So 1/2 is just a multiple, something being multiplied. So it's going to stay right there. And then the derivative of the natural log of 2x cubed minus 1, that's u prime over u. Okay, this is going to be the u. So 2x cubed minus 1. And in parentheses, it makes you feel better. Let's share the wealth. On top is going to go the derivative of that. So that's 6x squared. And that's it. This is the derivative. No multiple chain rule, product rule, quotient rule going on because we rewrote it first. The next thing I would do is I would simplify this. Okay, so for example, well, the 1 over x is going to stay. The 2 times the 2x, that is totally 4x, right? Minus the 6 and the 2, they totally cancel. Well, the 2 cancels. The 6 becomes 3. So now I have 3x squared on top. The 2 on the bottom is gone, and I have 2x cubed minus 1. And there is your derivative. No chain rule, no product rule, no quotient rule necessary. All right, derivative involving absolute value. So let u be a differentiable function of x such that u is not 0. And the reason u cannot be 0 is because if it's in the bottom of a fraction, if it's the denominator, we end up with a fraction that's no good, right? Undefined. Okay, so here I'm deriving the natural log of the absolute value of u. The beauty is that it's exactly the same as the other. The absolute value doesn't change anything. The derivative is u prime over u. Yay! Okay, so example 6, I'm going to derive a function with absolute value in it. So f of x equals the natural log of the absolute value of cosine x. This is still my u, right? If it makes you feel any better, you can list that stuff out. U is cosine x. So u prime would be the derivative of that, which is negative sine x. And then derive. So f prime of x equals u prime over u. And that's basically the derivative. But of course, we are expected to know stuff and to have learned things last year in pre-calculus. So an identity that you need to be able to very quickly acknowledge is tangent is equal to sine over cosine. And in this problem, I ended up with a sine over cosine. Granted, it's negative, but no big deal. So I have negative tangent of x. Okay, there you go. Next, example 7. This is a two-parter. So example 7. Oh, did I skip something? I did. Hold on a second. Okay, so derivative of log of, or logs rather. So if I have a function that looks like log of a of x, right? Or log a of x, the derivative is going to be, and it's it's not super easy, but it's not hard to memorize. It's going to be 1 over the natural log of a, right? A being the subscript, or the base of the log, times x. Now that's when you have the most basic function, where it's just x. Now, when x is more complicated, like 3x squared minus 5 or something like that, then it changes slightly, but it's very familiar because it's kind of like u prime over u, okay? It is u prime over u, but the difference is the natural log of a. Okay, so natural log of a times u. Now, that doesn't mean you can multiply the a and the u. So if you need parentheses, it would be wise to use them. Okay, over here I'm not multiplying the a with the x. Can't do that. The a belongs to the natural log. All right, so moving on. This doesn't want to cooperate. Huh. All right, example 7. So I'm taking the derivative of the log 3 of the square root of x. Okay, so u is all this stuff, right? So u is the square root of x. U prime is going to be the derivative of that. Now remember, square roots, we rewrite those as x to the 1/2 power. So when I derive that, I'm going to end up with 1/2 x to the negative 1/2 because I have to subtract a power. So that's that. And now I apply the formula. So the derivative of this is going to be u prime on top. Okay, so 1/2 x to the negative 1/2 power. I'm going to go ahead and I'm going to write that as 1 over 2 square root of x because that means the same thing. This is 1/2 times 1 over the square root of x. So 1 over 2 square root of x. Okay, I'm going to go ahead and write it. We're big boys and girls, right? Divided by the natural log of a, and a is the 3, times u, which is the square root of x. Now, I have a fraction inside a fraction, no bueno. We should know already that in order to get rid of the fraction inside fraction, what we're going to end up doing is we're going to end up multiplying the top by the reciprocal of the bottom. So I end up with 1 over 2 square root of x times the reciprocal of the natural log of 3 square root of x. So right now this is over 1, right? So yeah, flip it. So I get 1 over, and I'm going to go ahead and write the square root of x first so that we don't get it confused with the natural log of 3. And that's what I have now. And then simplify, please. 1 on top, the 2 stays. The square root of x times square root of x is one big fat x. And then the natural log of 3. And there's my answer to that. Okay, b. For b, this is my u, right? This is right here my a. U is cosine of x. Okay, so u prime is negative sine of x. And then derive. Okay, so the derivative is going to be u prime. So negative sine over x, sine of x, over the natural log of a, so natural log of 10, times u, which is cosine of x. And ooh, look, once again, sine over cosine. That's actually tangent, right? I wrote that earlier in one of the other examples, example 6. So what I really have is negative tangent of x over the natural log of 10. And there's my answer to that. Okay, moving on. All right, example 8. Find y prime if y equals the natural log of 6 times log with base of 6 of x. Okay, so these are tricky because natural log of 6 is a number. It's a constant. If I plug that in the calculator, I get a decimal. That is not a function. There is no x in there at all. It is a number. Therefore, it's just going to stay there when I derive because it's just a multiple. I am not deriving natural log of 6. You could do the product rule if you want, because this looks like a product rule. and you'll still get the right answer. But I'm trying to make you avoid doing that extra work. That is just a number. All right, now log with the base of 6 of x. That is the function I'm going to derive. So when I do derive, right, y prime, that natural log of 6 is going to be there because it's just a number. And I have to figure out what is the derivative of the log part. All right, so the derivative is, well, let me write the u. Okay, so u is going to be x. So u prime is uno. And of course, a is the 6 part, right? The little subscript, the base of the log is 6. Okay, so back to the derivative. Y prime equals the natural log of 6, because that is just a constant. It's going to stay there. It's a multiple. It's being multiplied. And then the derivative of the log part is u prime. So u prime is 1 over u, which is the natural log of a. In this case, it's also 6, times x, or u. But in this case, u is just x. And remember, the natural log, you're not multiplying the 6 with the x. And then looking at this, hopefully you're like, ew, I have a natural log of 6 on top and a natural log of 6 on the bottom. So they do cancel out. And my simplified version of my derivative is just 1 over x. Okay, now I don't have this example on your notes, but I was looking at your homework, and you're going to need it to answer number 19. So I called it example 9. If it's on your page, great. Okay. If not, then just watch. All right. So in order to do this problem, I'm going to use log properties, and there is one that allows me to actually kind of simplify an equation in a way by using natural log. Now, if you look at this equation, I have an x as an exponent, and it's actually the function itself, which is why I'm going to want to do this. So I'm simplifying first. Okay? I'm rewriting by using a log property. So I'm going to take the natural log, or the log of both sides. So natural log of y equals the natural log of x to the x power. Now, what this allows me to do is the exponent is now going to go in the front, and it's going to be multiplied instead of being an exponent. And that's what I wanted to fix. So the natural log of y equals x times the natural log of x. And that should actually look familiar because we've already done that. Example 3. Okay, so now this is my function that I'm going to derive. It's going to be derived implicitly because of the y. Okay, I am actually going to have to derive y. So now I derive. So derive both sides, right? I'll write it here. Derive. All right, so the natural log of y is going to be 1 over y. But because I took the derivative of y, I have to use dy dx equals. Okay, so x times the natural log of x. So it's u times v prime plus v times u prime. That's a product rule. So u, again, is x times the derivative of the natural log of x plus v times the derivative of u, which is 1. Like I said, we did that already, but I'm just doing it again. The x's do cancel out, if you see. So I have 1 over y dy dx equals 1 plus the natural log of x. Now I got to get the dy dx by itself. Right now it's being multiplied by 1 over y. So I need to multiply by the reciprocal of that, which is y over 1, to get rid of it, right? So all the other side, I'm going to multiply by y over 1, which is just y, right? Okay, so now I have dy dx equals y, I'll just write it in the front, y times 1 plus the natural log of x. Now, using our peepers, our eyeballs, very quickly, because I'm almost done. Come on, highlighter, doesn't want to work. Weird. All right, I'll do it in green. Y. If we look to the very beginning, we knew what y equaled. Y equals x to the x power. So I can actually go ahead and I can rewrite this equation by plugging in x to the x power for y. Okay, so I'm just going to move this. All right. So my answer, final answer, dy dx equals x to the x power times 1 plus the natural log of x. Okay, remember, I said that I replaced the y with what it originally equaled, and that is my derivative. All right, do your homework. Thank you very much.